Uh, Thank you. Firstly, I would thank the organizers for providing me this opportunity to be present at this wonderful workshop and talk about my work. So, following today's first talk from the morning session, I have slightly changed the title of my talk by putting quotation marks after hydrodynamics. But so this is some work that I've been working on, and some of it is done, some of it is in continuation with Professor Blazo, who is here, Sunil, who is here, and um, collaborators from OSU and North Carolina. Yeah. So the purest notion of hydro is that it describes evolution of conserved currents, energy momentum tensor, or any conserved charge current in terms of macroscopic variables like temperature, flow velocity, chemical potentials, and their gradients. These gradients are accompanied by transport coefficients like the coefficient of shear viscosity, bulk viscosity, or charge conductivity. And this notion of hydro, which was emphasized today, it should be distinguished from Israel Stewart-like hydrodynamic theories, which I will, uh, in short, call ISH throughout this talk, where the dissipative components or the fluxes of these conserved currents are promoted to dynamical degrees of freedom. So this deviates from the standard notion of hydro. The thing is, it is these Israel Stewart-like hydro theories which have been remarkably successful in describing intermediate stages of heavy ion collisions. What research over the years have shown that Israel Stewart-like theories derive from kinetic theory. It seems to work even when a fluid is not close to equilibrium. Now, however, how well it works, that depends on how well a certain truncation scheme is implemented, which is the main topic of this talk. And so I am interested in understanding and talking about how to choose an appropriate scheme for the to derive this Israel Stewart-like hydro equations. Yes. Oh, okay, okay, sorry. Yeah. Okay, yeah. Okay, so I'll quickly go over the standard framework in which one gets to Israel Stewart-like hydro theories from kinetics. So consider a system of weakly interacting classical particles whose description is given by a single particle distribution function, which gives the density of particles in phase space. The evolution of this distribution function is governed by a Boltzmann equation, where the right-hand side CF, um, it includes the effects of interactions. That is how it describes the interactions between these particles. Now, the main objects of interest in hydro are these conserved currents, like the energy momentum tensor or charge currents. Now, these are related to this distribution function because these are just certain moments of F. For example, here, T mu nu is this second order moment of this F, and which one can decompose in the standard way. So these terms in red are the dissipative components or the non-equilibrium parts of this energy momentum tensor. This is the bulk viscous pressure, capital pi, this pi is the shear stress tensor. And I use some standard notations. This is the projector which was discussed before. So for example, when this distribution function approaches the local equilibrium form, then T mu nu, all these non-equilibrium stresses goes to zero. So these off-equilibrium parts of the conserved currents stem from the deviation of the distribution function from its local equilibrium form. So there are these conservation equations, conservation of T mu nu. These describe the evolution of temperature and flow velocity, which are coupled to these non-equilibrium parts of T mu nu. Now, the standard way to derive it has been done way back by Denicol and collaborators. There, we have the exact definition of this bulk viscous pressure in terms of this deviation from local equilibrium, similarly for the shear stress tensor. Now, what one needs is also evolution equations for this bulk and the shear. So this is again obtained by applying a sort of co-moving time derivative on both sides and then using the Boltzmann equation. So just to set the stage, I mean, there are certain notations that I use, which I'll just describe. So this sort of angular bracket, this projects a tensor to the symmetric traceless part of it. So shear stress tensor by definition is symmetric, orthogonal to U mu and traceless. So, okay. So what this does is, now we have to uh, determine some, we have to work with some collisional kernel. So for this purpose of the talk, I will take a very simplistic collisional kernel, which is given by this relaxation time approximation, where the assumption is that whatever interactions between the particles, no matter how complicated, they try to drive the system towards local thermal equilibrium over some time scale tau r, which is the relaxation time. So if one takes this form of a collisional kernel and implements this strategy that was laid out, one obtains sort of exact evolution equations for the non-equilibrium currents. Exact in the sense of that, okay, I mean, there are no approximations that have been done till now, other than assuming that it's governed by kinetic theory with a collisional kernel like this. Okay. So the thing is, here we see several terms. For example, theta is the local expansion rate of the fluid. Sigma is the velocity stress tensor. And there are terms in red which are not related to any components of T mu nu that we have seen so far. So in some sense, this equation for the bulk pressure is exact, but it is not closed because this involves couplings to higher order moments of the distribution function. And similarly, this feature extends to the shear. So as I said, so this equation is not closed because of coupling to these sort of non-hydro moments of the distribution function. Right? So in order to truncate this equation, we need to decide on what is an suitable approximation for the distribution function that one can implement. Right? So till now there have been, I think, yes, okay, yeah. So there are several standard approximations that are done. For example, in the GRADS approximation, which is widely used in our field, one assumes that this distribution function one can just expand it in powers of the particle's momenta. So one expands it, and then one determines these coefficients by saying that, okay, this form of this off equilibrium correction should yield me the values of T mu nu at that instant. So this is how one determines these coefficients. And in this way, in the grad scheme, one obtains a certain form of this off equilibrium correction to the distribution function. Once one obtains this, one can just plug that in this definition and close the system of equations. Right. Another widely used form of this delta F is the one given by this Chapman and Skog-like expansion from RTA. So what here one does is assumes that a derivative like expansion works, and one expands this delta F up to first order in gradients in the velocity gradients. And so then one does a little bit of gymnastics with this. From here, the evolution. From here, the definition of the bulk and the shear stresses are obtained. Then one puts them back. So basically replaces wherever you see theta, you replace it with this bulk. Wherever you see the velocity stress tensor, you replace them with the shear. And this gives a different form of the delta F correction compared to the grad scheme. For example, this is quadratic in momenta. And here there are terms like the energy of the particle in the rest frame, which are downstairs. Right. So one can then use this to truncate the system of equations. Right. Yeah. Now, the third thing I will discuss about is one that is tailor-made to sort of describe heavy ion collisions at the early stages of the expansion. So here in heavy ion collisions, as the medium expands rapidly along the beam axis, there is a large pressure anisotropy that develops. Yes. Yeah. With Oh, I took it. Okay. Mm. I okay. Yeah, this I cannot just say this at the top of my head, but the philosophy is yeah, yeah, that that one just takes this, plugs it back, and yeah, by dazzling teeny, yeah, 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 yeah. Okay, right. So hmm? Yeah, yeah, yeah. Yes. So the third class of truncating distribution that I'll talk about is this form that is given by Romatzke and Strickland. So what this is tailor-made for heavy ion collisions because there the early time is characterized by rapid expansion along the beam direction. This rapid expansion gives rise to a strong anisotropy in the pressures, the longitudinal and the transverse pressures. And the idea here is that if one has to capture that sort of extreme conditions, it is better to expand the distribution function not about local equilibrium, but around an distribution function that captures this momentum space anisotropy. Right? So, for example, here this parameter captures the anisotropy between the longitudinal and the transverse pressures. But so this philosophy has given rise to anisotropic hydrodynamics and several variants of it. But I must emphasize that this is obtained by keeping this early stage heavy ion collisions in mind. It may not hold for generic flow profiles where the expansion is of a different kind. Right? So why a new truncation scheme? So GRAD assumes that this delta F should be expandable in powers of particle momentum, which is there is no sort of strong basis to it, right? And Chapman and Skog delta F, which assumes that it's an expansion in gradients, it should not be valid too far from local equilibrium. And importantly, both of these sort of corrections, once the momenta becomes large, then the total distribution function becomes negative, which is unphysical because in kinetics it gives the density of particles which cannot become negative. So, and also one finds that this resulting macroscopic framework breaks down in certain flow profiles. As I said, the Romatzke-Strickland ansatz, it does not become negative and can handle large deformations, but its form is ad hoc. I mean, it's an ansatz saying that okay, we can just do it to capture something about the nature of the expansion that is encountered. Okay. And we found that it is not possible to sometimes describe large bulk viscous pressures using this, and it might not be just possible to model arbitrary flow profiles using this ansatz. So what we have in mind is we aim for a truncation scheme that leads to a framework which may work both near and far from equilibrium, and it involves as less uncontrolled assumptions of the microscopic physics as possible. So, right. So essentially, we want to reconstruct a delta F solely using quantities appearing in T mu nu, like the energy density in the rest frame, the flow velocity, the shear stress, and the bulk viscous pressure. Now, this is in principle impossible. I mean, it's impossible to just only from knowledge of T mu nu to build to reconstruct the distribution function. However, what is the best guess, right? So, so this kind of question was answered, I mean, was pondered upon long back by Jaynes. So that the least biased of all distributions that uses only the information provided by T mu nu is the one that maximizes the non-equilibrium entropy density of the fluid, subject to constraint that this distribution function instantaneously satisfies the components of T mu nu at that point. Now, this form of the entropy, this F log F, it is very similar. It comes from this Shannon definition of the entropy, P log P, which So when one converts from this probability to single particle distribution function, one gets this extra factor of f. So this entropy, this form of the entropy density, it does not assume proximity to local equilibrium, but it assumes that the particles are weakly interacting. No. Oh, this one does not include quantum statistics, but one can readily, you can easily just do this 1 plus f log 1 plus that can be easily done. Right. Right. Yes. And the basic idea why we call this least bias is, I mean, is the age-old idea that we say we have a system with a given by a macro state specified by the energy, volume, and the number of particles. The system can be in a variety of microstates which are consistent with this macro state. And then one can assign in general, any probability distribution to these microstates. But the probability distribution where all such microstates that the probability distribution where we say that all microstates consistent with this given macrostate are equiprobable, that's the least biased choice. And that also maximizes the entropy P log P. So this is why we sort of, I mean, it's referred to this as the least biased distribution function. Right. So then the way to do it is then quite standard. We have this definition of the out of equilibrium entropy. We add Lagrange multipliers corresponding to whatever information we have about the system, that is the energy density in the rest frame, the bulk, the total isotropic pressure, and the shear stress tensor. And then we extremize or minimize this functional entropy density. Right? And then this yields this exponential form for the solution of such a distribution function, which we call the maximum entropy distribution function, where you see this capital lambda is capital lambda, lambda pi, and this gamma. These are the Lagrange multipliers corresponding to this information, the energy density in a fluid cell, the isotropic pressure, and the shear stress. So, and one can see that if locally at any point we see that the non-equilibrium parts have vanished, for example, if the shear stress is 0 and the bulk viscous pressure is 0, then these parameters go to 0 and we recover the Boltzmann distribution. Right. Right. Then the immediate question to ask is, okay, if this is the distribution with which we want to truncate our system of equations, when the system is close to equilibrium, what does this distribution function look like? So again, we just expand it, assuming that the shear and the bulk stresses are small, and one can do this sort of calculation. And then what one finds out is near equilibrium, the maximum entropy distribution essentially reduces to the Chapman-Enskog like correction that was obtained before for this RTL-like kernel. It is interesting to note that when we talked about this Chapman-Enskog correction, that used the information that this collisional kernel is like given by this relaxation time approximation. But the maximum entropy, this framework, it has no idea about what the collisional kernel is, right? Because it only uses information about the components of T mu nu, right? It's intriguing to note that it reduces exactly to the Chapman-Enskog expansion. But of course, if your relaxation time in the RTA depended on momenta, then this would not hold. But yes. 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 Yes, indeed. Actually, RTA, we have, there is some sort of jugglery that is done, because the thing is, if you strictly stayed within this gradient expansion, then you would not get what we are getting, right? But then what is done is, it is assumed that, okay, if you can rewrite this expansion rate and the velocity stress in terms of this sort of dissipative corrections, that is why your tower has gone away in this expansion. Yeah, yeah, yeah. So that express, yeah. through that. Now, if this step was not done, then they would not match. Yeah. Yes. 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 Yeah. Because the maximum entropy result doesn't know about the collision kernel at all. That, yeah. Yeah. Okay. So, right. So there are some nice features of this distribution function, so which we write here in the rest frame of the fluid. So that is why all these factors of u dot p have just become the energy of the particle. So this scale lambda, it plays some role near equilibrium similar to an inverse temperature. Lambda pi captures isotropic deviation from equilibrium, and this Lagrange multipliers gamma, it captures anisotropic deviation from equilibrium. So this gives rise to some shear stress. Now, because it's in exponential form, it is positive definite for all momenta. It is important to note that, once end of the day, one can rewrite these multipliers in terms of the shear and bulk stresses. If one rewrites that and then just expands this exponential, one would find that this sort of maximum entropy, it generates all orders of shear and bulk stresses. So it has some nonlinear dependence on this shear and bulk stresses, unlike the grad or the Chapman-Enskog, where it is truncated at, say, order just pi or pi mu nu or capital pi. So this, right. And this sort of idea has been pursued before in non-relativistic context back in '96. It has been also pursued, but in a very different form by Calzetta in 2019. Right. So roughly, yes. So there is a requirement for this entire thing to drop sufficiently fast at large momenta. So lambda pi in itself, I'll come to that sort of yeah, one example that right. Okay, so yes, but okay, so at each step we have all these Lagrange multipliers which we have to rewrite in terms of the bulk and shear stresses. So one might think that, so this has 5 independent components, this is 1, and so there are 7, and one needs to rewrite them in terms of the local energy density, shear, and the bulk. And one may think it's a very non-trivial inversion problem, 7-dimensional problem, but one can make simplifications, because although the full nonlinear problem requires an inversion of 7 parameters, which is numerically a bit non-trivial, but what one finds is one can show that this shear stress tensor in the local rest frame of the fluid is just a series in the matrices gamma, which are the matrices of the Lagrange multipliers. And then that means that this shear stress in the local rest frame commutes with this gamma. So they are simultaneously diagonalizable. And because shear stress is symmetric, it has real eigenvalues and admits orthogonal eigenvectors. So what it means is, if one just finds the eigenvectors of pi, then one can use it to diagonalize pi. This also diagonalizes the matrices, the Lagrange multiplier matrices. So all in all, the basic point to say is, instead of sort of solving for 7-dimensional inversion problem, this trick can be used to reduce it to a 4-dimensional problem. So 2 for these Lagrange multipliers for the shear stress, 1 for the bulk viscous pressure, and 1 for the energy density in the rest frame. So after all this, just a recap. So what this framework does, so we evolve the components of T mu nu. Okay. So for example, we have the evolution of the energy density, the flow velocity, and then we have the evolution of the shear and the bulk stresses. These are coupled to higher order moments of F, which, of course, to know this full F, we need to solve the full kinetics. But then what we are saying is, just construct this maximum entropy distribution using instantaneous values of T mu nu and use it to truncate the system of equations. So, okay. Now the question is how well is it doing, right? So I'll talk about three tests of this maximum entropy framework. First, I'll talk about energy momentum evolution in Bjorken flow. So for very far off equilibrium initializations. So just a small review of, then Bjorken flow is applicable for the early stages of heavy ion collisions, and its boost invariance is manifest in, we'll use the coordinates where this flow appears to be at rest. The important just the thing to note is, because of this symmetry is apparent in this expansion, the energy momentum tensor has essentially three independent components: the energy density, the transverse pressure, and the longitudinal pressure. Right. Okay, so this I'll just right. So these three components, we have exact evolution equations that one can get from kinetics. So again, in this simplified expansion profile, the distribution function expands in a certain manner. So using this, one can equivalently rewrite the evolution of the energy density, the longitudinal pressure, and the transverse pressure. As expected, this is not closed because these equations couple to higher order moments of the full distribution function. But what we do is, at each time from the values of E, PL, and PT, we reconstruct the maximum entropy distribution and then use that to close these moments appearing here. Right. So that's the framework in Bjorken. Okay. So first results for the case where particles are massless. So the bulk viscous pressure is 0. Yes. 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 Uh, so yes. Yes. In in the sense that if you say write out the evolution of the shear stress, say just in Bjorken, right? In Israel Stewart, you would have this relaxation term and some terms coupling pi to the expansion rate, by tau, and there it would stop. But here, if you just expand out, it will contain all orders of pi, right? Infinite. It's a, it's a yes, but if you ask that, okay, if I want to compute it near equilibrium and want to extract do a gradient series, right? Will that agree with kinetic theory to all orders? Of course not. But yeah, yeah, yeah. So right. Yes, yes. So this we do numerically. So basically, yeah, just root find to obtain these Lagrange multipliers, and after finding it, just do the integrals. Yeah, right, right. So in the conformal Bjorken case, we show the evolution of this shear stress normalized by the enthalpy density of the fluid to make it dimensionless as a function of the Bjorken time scaled by the relaxation time of the system. So these dotted lines are exact solutions of kinetics. So basically, these are obtained by solving this RTI Boltzmann. Exactly. Yes. 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 Yes, probably. What can be done at least in Bjorken is that you have this evolution of pi bar, which is pi by epsilon plus p. So that is a function only of tau by tau r, right? So there is one term which is like some function of pi bar, right? Uh, and and everything comes out with a 1 over tau. So whether you can just yeah bring it back and say, okay, I only want transport coefficient which is varying as a function of pi bar. In Bjorken, at least, I think it can be done. Yeah, right, right. So okay, so these dotted lines are solutions of this kinetics, and the dashed lines are obtained using this truncated procedure of maximum entropy. And one sees that it is very nice agreement with kinetic theory results, even when the shear stress is quite large. So it's the maximum allowed value of shear stress in kinetics for this flow profile is minus 0.5. So it has gone almost to minus 0.45. Now, this kind of agreement between kinetics and sort of macroscopic framework is not new. For example, Li Yan and Professor Blazo has explored this, and they have found that one need not do this all order sort of theory, but maybe change a higher order moment in order to capture some early time fixed point of the system, and that exactly gets this sort of behavior right. But the thing is, there you have to put in some more information about the flow profile. Maximum entropy doesn't really care about what the flow profile is. It just knows instantaneously what is my component of T mu, and from there it just gets the evolution. Okay, and so here I just plot just to show how the Lagrange multipliers evolve. There are no surprises. This lambda, which plays a sort of role of an inverse temperature. At early times, there are quite a lot of differences, but at late times, this is when the system equilibrates, it becomes like 1 over T. So no surprises. Also, this parameter gamma, which characterizes the deviation from local momentum uh, isotropy, it decreases as the system thermalizes at late times. So, okay. Now we will come to something more interesting by putting in the masses of the particles. So now there is a bulk viscous pressure in addition to the shear stress. So this is still Bjorken, but massive particles. So now there are two components of these dissipative fluxes. And here, um, yeah, so the top panel evolves the bulk viscous pressure normalized by the enthalpy density as a function of the Bjorken time. And the second one evolves the shear stress tensor. Now, these solid lines are exact solutions of the Boltzmann equation with RTA. And these dashed lines are obtained not by maximum entropy, but using second order Chapman-Enskog like hydro. What one clearly sees is strong deviations between the exact solutions of RTA, Boltzmann, and the second order theory, which is not surprising. I mean, it's not meant to work in situations which are very far from local equilibrium, and it does not. And I mean, here we plot the evolution of the effective longitudinal pressure of the system as a function of tau over tau r. What one sees is the kinetics. This has been well known in Bjorken flow for quite some time, that in kinetics there is a sort of rapid decay of initial conditions to some universal curve, even when the system is far from local equilibrium. So tau over tau r less than 1 means collisions haven't had enough time to isotropize the system. And the second order theory, again, here, not only does it not capture this sort of early time universality, but if one goes too far out of equilibrium, even the longitudinal pressures become negative in this theory, which is, I mean, in general, it can happen, but if it is supposed to mimic kinetic theory, then the effective pressure should not become negative. So roughly, just the thing is, standard hydro, not surprisingly, is not in very good agreement at when the system is very far from equilibrium. It does not describe early time universality accurately. But the moment one does this maximum entropy truncation, one sees that this sort of dashed lines which are obtained by this truncation scheme comes reasonably and very close, in fact, quite close to the exact solution of the RTA-Boltzmann equation. And the early time universality in this effective longitudinal pressure evolution is very nicely captured, and it's almost indistinguishable from the results of kinetics. So, okay. And now coming to Gabriel's question, if we look closely in this very far from equilibrium scenarios, how the Lagrange multipliers that are in the maximum entropy, how they are evolving, then one sees a curious feature. For example, lambda, one is inclined to think that lambda is some sort of inverse temperature. But one sees that far from equilibrium, it has even gone negative. But the thing is, lambda going negative doesn't mean that the distribution function has become ill-defined at large P. For the maximum entropy distribution to rapidly go to zero at large momenta, all that is required to hold is a certain combination of these Lagrange multipliers to be positive. Some combination of capital lambda, lambda pi, and gamma. So lambda pi does go negative and positive. It depends on what bulk viscosity one chooses. So one sees that this quantity sigma, which should be remain positive at all times, it indeed does, but far from equilibrium, this lambda cannot be identified as some inverse temperature. Now, what one might want to ask that, okay, what is the why is it becoming negative? What is the physical meaning? So the thing is, this total isotropic pressure in kinetics, which is the sum of the thermal pressure and the bulk viscous pressure, can be written is just related to the amount of momentum, that is flux here. Now, we were generating very large negative bulk viscous pressures, almost of the order of thermal pressure. Now, for that to be generated in kinetics, that means that the distribution function is the low momentum states are being populated. It's becoming very peaked in small momenta, right? So what maximum entropy distribution is trying to do is trying to mimic this behavior, but all it manages to attain is as momentum goes to zero, it has only this parameter lambda. So to somehow enhance this occupation of low momentum modes to get this large negative bulk viscous pressure, it makes this capital lambda become negative. So that is what he is trying to mimic here. Yes, always remains positive. Yeah, yeah. Yeah, yeah. Not in Bjorken. At least there. No, well, it satisfies a stronger condition than the dominant and weak, which is it satisfies a stronger condition. So this kinetic theory conditions of PL greater than zero, PT greater than zero, and energy density greater than zero, it will always satisfy the dominant, the weak, and all that, right? But it's not necessary that the satisfaction of this dominant condition will guarantee this kinetic theory positivity of pressure. So it's, yeah, I would say it satisfies those conditions. At least in here numerically, we never see violation, even though we initialize it at very extreme non-equilibrium situations. Right, right. Okay, so test number 2, so in Bjorken, the flow profile was such that it's an expanding profile in one direction, but at late time, the expansion rate, which is like 1 over tau, is decreasing. So essentially, what happens at late times, the relaxation rate or the interactions between particles wins over the expansion, and the medium thermalizes. So one might say, okay, what if one tries more extreme sort of fluid evolutions where the medium may not thermalize? Will the maximum entropy hold, or will it survive the test there, right? So we looked then into Gupser flow. So as I said, Bjorken assumes that the fluid expands only along the longitudinal or the beam direction, so there is no transverse expansion. In Gupser, the fluid expands in both the longitudinal and the transverse. And at late time, the flow profile is such that the transverse expansion dominates. In fact, the transverse expansion rate is 4 times the longitudinal expansion rate. So if one just does a simple calculation of how the temperature evolves in this Gupser evolution at late times, one finds that the temperature drops very rapidly. So from there, one can also estimate how the ratio of the relaxation rate and the expansion rate, how it grows. And what one concludes is that in Gupsar, it has been well known before too, right? I mean, that in Gupsar, at late times, the fluid expands so rapidly in the transverse direction that the Knudsen number doesn't decrease, but instead grows. So the fluid does not thermalize, right? So it's natural to test how well this maximum entropy truncation is doing in this sort of extreme flow profile. So just like Bjorken becomes very nice to analyze in Milne coordinates, where the flow fluid velocity appears to be at rest, Gupsar is can be analyzed in the so-called Gupsar coordinates characterized by rho. This theta is not the nothing to do with this angle, normal angle theta. It's a different one. But okay, so this rho plays the role of a Gupsar time, and yeah, so we essentially play the same kind of game in Gupsar, right? So we write down the evolution of the energy density and the transverse pressure. This is coupled to some higher order moment, and to truncate it, we use the maximum entropy philosophy. And then we come to I show some results here. So here I show the evolution of the shear stress scaled by the enthalpy density of the fluid as a function of the Gupsar time rho. So these green lines are exact solutions of the Boltzmann equation for this profile, and the red ones are solutions of second order hydro, right? So what is happening is initially is a longitudinal expansion that is dominating. So the shear stress becomes very close to 0.25, where the effective longitudinal pressure is going to 0. But then the transverse expansion picks up, and eventually the system is dominated by transverse expansion. So it goes towards the situation where the effective transverse pressure goes to 0. So which is being basically which is plotted in the right panel. So this is the evolution of the ratio of the longitudinal pressure to the transverse pressure as a function of this Gupsar time, right? So initially the longitudinal pressure drops, becomes very small, and then eventually the transverse pressure becomes very small, so PL over PT keeps on growing, right? Now, the main thing to see from this plot is that, I mean, the second order hydro clearly breaks down. Here, both the transverse and the longitudinal pressure becomes negative at different times. And so it works only when the fluid is close to equilibrium, PL over PT is small. Again, I mean, it's not extremely surprising. Second order hydro is not supposed to capture this sort of extreme scenarios. But then one might say, okay, let's go to third order hydro. Maybe that will solve. Yes, yes, yeah, yes, yes, yes. Oh, then it probably is the minus, the negative sign. I mean, it's just then the flipped. It's just flipped. Yeah, 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 yeah. Yeah, we had to play around with this. Yeah, it's just flipped. So, but yeah, here at least in PL over PT, you see that PL has decreased. Yeah, and then this has so right. Yes. Okay. Okay. So then, okay, one might think that okay, let's add one order more in the hydros and let's do third order hydro, right? So it does little better, but then at late times when the transverse expansion has really picked up, the third order hydro, this red line goes to a different point. And also you would see there is a missing curve here because if one with so far off out of equilibrium condition, one cannot even the equation cannot run the equations. It just breaks down. So okay, with this in the back of our head, let's look at what maximum entropy does. So these are the blue curves. Shows very nice agreement with kinetics, the green one, right throughout the very late Gupta times of 10. So yeah, when one looks more carefully in the evolution of these anisotropies in the pressure in the longitudinal to transverse anisotropies, one sees some differences, but this is log scale, but um, it is, if you compare it to what we saw for the hydro, I would say it's a good improvement. And we checked that these pressures always remain positive. Okay, so finally, in the last 15 minutes, I will come to something that we have been working on recently. So this is, we wanted to basically understand how the matter, how the matter transits from a free streaming or kinetic-like behavior to a hydrodynamic regime when one includes the transverse dynamics in the picture. So in heavy ion collision, matter expands almost boost invariantly along the beam direction. So it makes very hard for the collisions to sort of bring the system thermal equilibrium because there is so fast expansion already. In contrast, in the transverse plane, the matter is roughly at rest initially to start with, and then explodes into vacuum. So the simplest problem we thought that one should understand is how just a sort of finite slab expands into vacuum, right? So this is so what we did is we took a slab of matter. This is very similar to the Riemann problem. Slab of matter in one direction is infinite in the other two directions, and we just let it explode into vacuum, right? And we study this in two extremes conditions. One, where the particles which are constituting the fluid are just assumed to be non-interacting. They just fly apart without interaction. This is the free streaming. And in the other extreme, where the particles interact, suffer infinite collisions in their lives, and which is the limit of ideal hydrodynamics, where the relaxation time has gone to zero. It instantaneously thermalizes. So if one can just run the code or just do a simple analytical calculation to see that in these two extreme scenarios, the main difference is that, okay, in both these cases, when one lets the system explode, there are rarefaction waves that propagate inward into matter. When the particles are non-interacting and they're just flying apart, these rarefaction waves move inward at the speed of light. In the other extreme case, when these particles are interacting quite a lot with each other, what it does is it slows down the propagation of this rarefaction wave to the speed of sound. So you can see that the green one has hit the center of the slab, whereas here in ideal hydro, it is still to reach the center. And the other thing that happens is if there are no interactions, it's quite smooth. But in contrast, in ideal hydro, a sort of shock fronts develops. Now, if we solve kinetic theory at finite tau r, which is in between these two extremes, just solve it, then there is nothing surprising. What one finds is kinetic theory, if one sees that these curves, which are these solid curves, right? And this other extreme is with a very large relaxation time, which is essentially meaning that the particles are just flying apart, there are no interactions. So kinetic theory smoothly interpolates between these two extremes, right? So with this in mind, let us try to see that how maximum entropy does in sort of capturing certain aspects of this extreme sort of evolutions. So here what we have these conservation equations for the energy density and the momentum density. The momentum density equation is coupled to a higher order moment, is coupled to the xx component of T mu nu, and the xx component of T mu nu is coupled to a higher order moment. And then what one can show is, okay, in this profile, the maximum entropy takes this sort of form. Now, what was shown way back is by Kurkela, Wiedemann, and others is, if the particles are massless, and if we are interested only in the evolution of T mu nu, then one need not solve for the full distribution function f, but one can just integrate out the magnitude of momenta and solve for what we call this capital F, which just gives the distribution of energy of particles, which gives the angular distribution of energy of the particles. So with this in mind, what we wanted to see is how well the maximum entropy distribution is approximating the exact kinetic distribution, right? So what we do is, again, we started from this Riemann slab and let it explode. We solved kinetic theory with a certain relaxation rate, which is, not too small, so it differs from the extreme hydro limit. And we look at a profile at time 4 Fermi, and then zoom in at 3 different spatial positions. of x of 3 Fermi, 5 Fermi, and 7 Fermi. 7 is right near the edge, right? And there we plot this quantity, this quantity f, which gives the angular distribution of energy of the particles in the rest frame of the fluid, right? So these solid lines, the dashed lines are the exact kinetics, and the solid line is how maximum entropy is basically trying to mimic this sort of distribution function. So the thing to note is, if we were doing perfect ideal hydro, that is if tau r was very small, then in the local rest frame, no matter how close we are to the edge, the distributions would be flat, because in the local rest frame, the distribution function is isotropic in momenta, so it should be flat in this variable, which is the angle. But here, because it's not very close to hydro, one sees deviation from a flat distribution throughout, and the deviation seems to grow as one approaches the edge of the matter here, right? And so what one sees is, near the edge, you see differences between the maximum entropy and the exact distribution function. But again, it is trying to capture some average property of the exact thing. So with this, we went ahead and just solved this maximum entropy truncated system and compared it with the kinetics. So the solid lines are obtained using this maximum entropy, and the dashed are exact kinetic theory solutions. You see some differences at the edge and at the point where the waves have collapsed. So, I mean, in one sense, it is not, I mean, maximum entropy will, I don't think it will ever be able to just get the free streaming limit right, because it will have, I mean, it's not the exact solution of the Boltzmann equation. So if the particles are not interacting at all, it cannot exactly capture the dynamics. And this one would see more and more if you just increase the tau r even more. But at least it captures certain aspects of this sort of very extreme evolution. So with this, and this is work in progress, so yeah, there are more things to be explored. And with this, yes, in the last 5 minutes, I have only talked about using maximum entropy as a dynamical framework. But in heavy ions, we also have this problem of freezing out. So when the system expands via hydrodynamics, but eventually becomes too dilute for hydrodynamics to apply, at that stage, one has to change the language and convert the hydrophiles into particles. And there also one faces the same sort of problem, I mean, same sort of questions, that what is my best guess for a distribution function at the freeze out, given that I have certain information about the hydro variables. So there too, one has the same sort of uh, ambiguities about what to use for the freeze out distribution, whether it should be grad, Chapman and Skog or something. And I think there also one can use this maximum entropy principle to as a sort of least biased choice of what is the microscopic distribution given the macroscopic information. So yeah, I'll not talk about that here, but so I'll come to my summary. So Israel Stewart-like hydro can capture certain aspects of T mu nu evolution, even when the system is not close to equilibrium. So I talked about the derivation of a far from equilibrium sort of macroscopic theory. Of course, always keeping in mind that the background is as if can be described by kinetics. If it's not kinetics, then none of this works. So this scheme tries to introduce as less ad hoc assumptions about the flow and uses information only contained in the conserved currents. We showed that it quite nicely describes kinetic theory results for T mu nu, for Bjorken and Gupsar flows, both near and far from equilibrium. It models, not bad, nicely the expansion of a finite slab of matter. Now description of T mu nu in more complicated flow profiles are being explored. So thank you for your attention. Yeah. Yes.
Excuse me, may I ask a question?
3 over 4 pi. Yeah. No, it's Knudsen number is not only dependent on eta over s, right? It's also how strong the gradient. Yeah. Yes. Density frame is solving it at eta over s 20 over 4 pi, but what it is solving, I don't know, right? No, no, no. In this, all I have in mind is some sort of it is supposed to mimic kinetic theory for Timianu evolution. I'll not even talk about eta over s, right? Yeah, yeah. At this point, RT evolves. At what eta over s? At eta over s, it matches with QCD kinetics. I thought it's a first order expansion. Density frame. At arbitrarily large eta over s. I see. No, no, that is eta over s, but Knudsen number is yeah, yes, yeah, yes, yes, yes. No, but what Knudsen number? I mean, is the Knudsen number much larger? No, no, 0.6, 0.8. So here you see the Knudsen number, right? Yeah. So if you see, look at this Knudsen number. Take the inverse of this, right? It's 10, right? So eta over s is not the main thing that I'm concerned about here. Yeah. Yeah. Right. Yeah. Yeah. Oh. Right. So at least for conformal hydro, Chapman and Skog and DNM are the second order is coincides, right? It, um, yes, 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 yes. No, no, exactly. I didn't show a plot for the entropy, which involves all these higher order moments. So that if I plot the entropy evolution using this scheme, then it is differs quite a bit from the kinetic theory. For example, in kinetic theory, I can go to the extreme limit where there is no entropy produced. But this is not a solution, right? This will produce some entropy even there. So in this, yeah, indeed.
Can you hear me? Okay. Uh, I just would like to ask, have you considered the possibility of entropy production by the current, diffusion current, and so adding another possible Lagrangian multiplier?
Yeah, that's a good point. If I have not considered it, and if one considers that, probably that would encode information about the collision kernel, because entropy production would depend on the collisional kernel. Here, the framework doesn't care about that. So yes, that's a good suggestion. I have not considered it.
Okay, okay. Thank you.
Yes. So to what I have done thus far, no. Uh, that is related to that what Gabriel was asking, right? Um, that whether you can just absorb all of it and redefine certain coefficients. But so if I understand correctly, right, that say here, I mean, here one could have written the equations in the form of pi, small pi, capital pi, and so on, right? But and then this object, if one did some, one could have expanded also in small pi, capital pi, right? So then, um, are you saying one can combine all of them and interpret something in a different manner, or yes, yes, right? So that what I understand is that is a, I mean, we can write the equation in that form to make it similar, very similar to what we have for Hydro and Israel Stewart, right? I mean, for example, here, this has none of the sort of coefficients eta, zeta appearing here, right? But I mean, if I, after this truncation, I can just rewrite everything in terms of small pi and capital pi, even recast this. And then you're saying I can, because you see here, there is almost, there is no, nothing about eta or zeta. I don't even, yeah, in the full equation, for example, so maybe this has slightly more, right? Yeah, 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 yeah. Mhm. Yes, 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 yes. Yeah, yeah. Mhm, mhm. Yes, at some point I had plotted this sort of contribution as a function of the shear, right? And then, I mean, all it was doing is at the two extremes, it was just ensuring you get to the right sort of, you don't make PL or PT to be just zero or something. It was, but uh, which is seems quite similar to what this approach is, right? You redefine your sort of thing so that you ensure that it never goes out of the kinetic theory bound of this. Yeah, 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 yeah. Actually, this is, sorry, for example, the plot of bulk pressure and shear stress. And these blue solid lines are the regions beyond which, I mean, kinetic theory, whatever you initialize within this thing, it will never go out of these sort of regions, right? And standard second order hydro, if you make it, if you start at very far from equilibrium, it sort of goes out of these bounds. But the moment you do this sort of this truncation maximum entropy, you see all of this is nicely within. Yes. No, yeah, I have not performed a stability analysis on this. All I can say is near equilibrium, it would be the same sort of stability analysis as second order, but could you please say that again? Sorry, could you say that again, please? That yes, yes. So at this moment, I don't know. I have not done a stability sort of check. Which let's see. There is something in the in the chat. There is something in the chat. That's okay. Thanks. Okay. Okay. Yeah. Yeah. Yeah.